At some point over the past several years, your fingernails quietly formed fine vertical ridges that were never there when you were younger. These lines stretch from the base near the cuticle all the way to the tip, catching light when you tilt your hand just right. There was a time when your nails were smooth and unnoticed, but over time these lines appeared and gradually became more visible. Nearly everyone past a certain age has them, and most people simply accept them as a normal sign of aging, placing them in the same category as reading glasses or stiff joints in the morning. What often goes unnoticed is that these lines began forming months before they ever appeared, deep within a layer of living tissue you likely never paid attention to. The surface pattern is essentially a record of what that hidden tissue experienced during the months it took for that section of nail to grow outward. The real question is what that record reveals. Most people notice these ridges by chance. A thread catching on a sweater, a nail that no longer polishes to a smooth shine, or the faint drag of a fingertip across paper. You notice it briefly, assume it is simple wear and tear, and move on. But the real explanation lies far beneath the surface. To understand it, you have to focus on where the nail actually forms, which is not the visible part at the fingertip. The nail you see is no longer alive. Every cell within it stopped living long before it reached the edge you can tap against the surface. It was all created in a small, crescent-shaped area of active tissue hidden beneath the cuticle, known as the matrix. That is where the entire story is written, out of sight beneath the fold of skin at the base of the nail. What you see at the tip is simply the final product. The actual process happens about a centimeter back, under the skin, continuously working whether you notice it or not. The matrix has a single task. Its cells divide, flatten, fill with a tough protein called keratin, die, and are then pushed forward by new cells forming behind them. Your fingernail is essentially the byproduct of this process, steadily moving outward at a slow but consistent rate, roughly the width of a few hairs each week. Growth is gradual. It slows with age, and it varies from person to person, which is why hands do not age identically. If you calculate this pace, an interesting fact appears. The part of your nail at the tip today was formed near the cuticle around 4 to 6 months ago. In other words, you are looking at something created months in the past. This steady production depends on a limited supply of dividing cells that must constantly renew themselves. Every new layer of nail requires cell division, and each division demands energy, accurate replication of genetic material, and a steady supply of nutrients delivered through the blood. If any part of that process slows down, the entire system adjusts. The matrix operates close to its limit, which is why even a small disruption in supply quickly shows up in the nail structure. This is where the body reveals subtle changes most clearly, at points operating near their capacity. The matrix is one of those points. A system working at its edge reflects even the smallest imbalance. What most people never learn is that the matrix is not a single uniform surface. Instead, it is divided lengthwise into narrow sections, each functioning like its own production line, creating thin strips of nail side by side. Imagine multiple parallel lines in a factory, each producing the same output, but running at slightly different speeds depending on its resources. When all sections work evenly, the nail surface appears smooth and uniform. But if one section slows while another continues at the same pace, the resulting strips differ slightly in height, and where they meet, a ridge forms that becomes visible on the surface. Seam, and that seam moves outward with a growing nail, appearing as a subtle raised line. That line is the ridge you see. Every vertical ridge represents a boundary where one column slowed compared to the one beside it. In simple terms, a ridge is a visible record of production line that lost pace, which naturally leads to the next question. What determines which lines slow down and which continue steadily? The answer lies in the body's circulation. Each of these microscopic production lines depends on a blood supply, delivered through some of the smallest vessels in the entire body, woven to the thin layer of skin just above the matrix. Every strip of dividing tissue relies on its nearest vessel for essential resources: oxygen for energy, glucose for fuel, amino acids to build keratin, and trace minerals that support cellular function. The speed of each strip is directly tied to performance of the vessel feeding it. If that vessel weakens, the strip has no alternative source to compensate. To understand this further, it helps to examine how blood actually reaches this area. Instead of flowing through a single large channel, it arrives through a tightly packed series of tiny looped vessels. Each one rises toward the tissue, curves at the top, and descends again, arranged side by side like fine teeth of a comb rather than a wide stream. As described in research by Johann de Backer, the matrix operates in this looped, column-based pattern, where each vessel supports only the strip directly above it with minimal overlap. This structure explains why the system behaves the way it does. Because each loop functions independently, one can weaken or fail while the neighboring loop continues working normally. When that happens, the strip above the weakened loop receives less support, while the adjacent strip continues unaffected. These isolated disruptions create the uneven growth that forms ridges. At this point, the explanation extends beyond nails. These tiny vessels age in the same way as larger arteries throughout the body, following identical biological processes, just on a scale too small to observe directly. The inner lining of blood vessels, known as the endothelium, gradually loses its ability to produce nitric oxide, a molecule responsible for signaling vessels to relax and remain open. As this ability declines, vessels become slightly narrower and less flexible, increasing resistance to blood flow. This same change occurs in the fine vessels, supplying the nail matrix. Their reduced flexibility limits the delivery of nutrients and oxygen to the cells that depend on them. Alongside this, another slower process contributes to the effect. Sugar molecules circulating in the bloodstream occasionally attach themselves to proteins within the vessel walls. Over time, these attachments form strong crosslinks, binding proteins together into a stiff, dense structure. This gradual process, similar to the caramelization of sugar, alters the flexibility of living tissue, and once these changes occur, the body has no effective way to reverse them. The same mechanism affects other parts of the body, such as the lens of the eye, reducing its ability to focus, and the walls of major arteries, making them less elastic in these already stressed microscopic vessels. This stiffening further restricts blood flow. Some of these tiny loops may eventually close entirely. A third factor then compounds the issue. In younger tissue, the network of these loop vessels is dense, allowing nearby loops to partially compensate if one becomes less effective. Over time, however, the overall number of these vessels decreases. The dense comb-like structure thins, leaving fewer loops spaced farther apart. Each remaining vessel must then fully support its assigned strip without assistance. As a result, minor disruptions that once went unnoticed now lead to visible differences in growth. This gradual reduction in vascular support transforms what was once a smooth, uniform surface into one marked by ridges and variation. What begins as subtle chemical and structural changes within blood vessels eventually appears as a physical feature you can both see and feel on the surface of your nail. Even without naming it, you may already recognize the effects of circulation changes, the sensation of hands becoming cold and remaining that way longer than before, long after the rest of your body has already warmed up. A small cut on your fingertip takes noticeably longer to heal, while a similar cut on your arm might close within a day. Press your fingertip against the surface and watch it turn pale. Then notice how it now takes an extra moment to regain its normal color once you release it. All of these are signs of the same microscopic circulation, the same network of tiny loops gradually declining and revealing themselves in different ways. The fingertips sit at the very edge of the body's circulation, farthest from the heart, making them the first to feel any restriction in blood flow and the last to recover from it. The matrix exists in the same boundary zone, quietly recording changes that cold hands and slow healing only hint at. If you follow the effect down to a single strip, the picture becomes clear. A production line supported by a loop that has narrowed, stiffened, or disappeared begins to run short of oxygen, fuel, and raw materials. It slows down. Meanwhile, the strip beside it, supplied by a vessel that remains healthy, continues operating at nearly full speed. This difference between two neighboring strips, once perfectly synchronized, eventually appears on the surface months later as a ridge you can feel under light. A deeper ridge reflects a larger imbalance in supply between adjacent strips. A nail filled with ridges suggests multiple strips are struggling at the same time. The gradual increase in these ridges through your 40s and 50s, starting subtly and becoming more obvious, is simply the result of this tiny vascular network slowly declining, one strip after another, until the surface can no longer hide it. It is important to acknowledge a clear limitation here. The idea that each ridge directly corresponds to a single failing loop is strongly supported by anatomical evidence and aligns with clinical observations when doctors examine the living vessels near the nail base. Studies such as those by Hiroshi Nakamura and colleagues have shown a close relationship between the position of these loops and the ridges that appear. However, a perfect one-to-one mapping between a specific ridge and a specific failed vessel has not been definitively proven at the microscopic level. The overall pattern is well supported, but the exact pattern remains an informed conclusion based on structure, and it is important to distinguish between what is confirmed and what is inferred. These loops determine which strips fall behind, but what exactly are they lacking? What essential components carried in the blood does a dividing cell need to continue building nail? 3 key elements play critical roles, each functioning at a different stage of the process. The first is iron. Before a matrix cell can divide, it must replicate its genetic material, DNA, the detailed blueprint that guides every cellular function. Producing a new copy of this blueprint requires assembling specific molecular building blocks, and one crucial step in that process depends on a single enzyme. This enzyme acts as a bottleneck, the narrowest point in the entire system, through which all DNA replication must pass. At its core sits an iron atom, essential for enabling the chemical reaction that drives the process forward. Without sufficient iron, the step slows down significantly. As a result, cell division decreases, and the strip of nail associated with that cell line grows more slowly than its neighbors. Because every division depends on this iron-based mechanism, even a slight reduction in iron delivery from a weakened vessel can have a noticeable impact. The second element is zinc. Zinc operates in a different role within the cell, supporting proteins that function as precise switches controlling gene activity. These proteins must bind to specific regions of DNA at the correct time to ensure the right instructions are followed during nail formation. Their ability to maintain the correct shape depends on zinc atoms that stabilize their structure. Without zinc, these proteins lose their form and can no longer attach properly to DNA. As a result, the process of building keratin continues, but with slight inaccuracies. The structure of the nail becomes subtly irregular, contributing to uneven growth. Zinc is also used by many other cellular systems, meaning it is in constant demand. When supply drops, its effects are distributed across multiple processes, further weakening the overall efficiency of nail production. In this way, both iron and zinc shortages, even at small levels, can influence how evenly and effectively the nail matrix performs its task, ultimately shaping the ridges that appear on the surface over time. The nail becomes more fragile, and the ridges grow sharper because the quality of the material itself declines along with the speed of production. Iron determines how quickly the nail is formed, while zinc influences how well it is constructed. Then comes biotin, the third essential component, working at a different stage. Biotin attaches to a specific group of enzymes and acts like a carrier arm, helping transport necessary fragments, so those enzymes can build longer chains of fatty molecules. These fatty chains are important because the nail does not simply stack its hardened cells like dry bricks. Instead, it fills the tiny spaces between them with a soft, waxy, lipid-rich substance that acts like a binding cement. This material fuses thousands of dead cells into a single, continuous plate that resists water and bends as one unit. When biotin levels drop, this carrier system weakens. The fatty chains become shorter, and the cement holding the cells together thins out. As a result, the cells lose their tight connection, the nail plate weakens, and it becomes prone to splitting or peeling at the edges. At the same time, ridges appear more prominent because a structure that is no longer firmly bonded flexes unevenly across the underlying strips. In simple terms, iron controls the speed of production, zinc controls the quality of the material, and biotin controls the strength of bond holding everything together. Each plays a role at a different stage, and each deficiency leaves a distinct pattern on the nail surface. This distinction is what gives the nail its diagnostic value and allows careful observation to reveal deeper insights. When the entire body lacks iron, all production lines slow down together, resulting in a nail that becomes uniformly thinner across its width, with minimal ridging, more of an even fading than a patterned surface. Aging, however, produces a different effect. Instead of uniform change, it affects individual strips at different times as specific vessels weaken. This creates an uneven surface with ridges of varying depth, forming a textured pattern rather than a smooth thinning. Research by Claire Cashman and Daniel Sloan has demonstrated these connections between the appearance of the nail and underlying physiological changes, showing how the surface reflects internal conditions. For most people over the age of 50, vertical ridges are more closely linked to changes in circulation than to simple nutritional deficiencies. Nutrients explain what cells require, but circulation determines how consistently those needs are met. There is more information in these ridges than most people realize. Once you understand how to read them, the depth of a ridge indicates the degree of difference in supply between two neighboring strips. A deeply starved strip falls far behind its neighbor, creating a pronounced ridge, while a minor shortage results in only a faint line. Depth reflects severity. Spacing reveals distribution. A nail with only a few widely spaced ridges suggests isolated areas of reduced supply, while a nail densely covered with ridges indicates widespread decline across many strips. Together, these features transform what might seem like simple texture into a kind of visual map. Each nutrient leaves its own signature, and each disruption adds another layer of information. When you stop focusing on individual ridges and instead observe the entire nail from base to tip, it reveals something even more interesting. It acts like a timeline. The section from the cuticle to the tip represents several months of growth, arranged in order, with the newest material near the base and the oldest at the edge. This sequential growth makes the nail readable in terms of time. For example, a brief but intense illness can temporarily disrupt all production lines at once, leaving a single horizontal groove across the nail. This feature, known as Bow's line, moves outward as the nail grows, marking a specific moment in the past. Similarly, a prolonged period of poor nutrition creates a wider zone of thinner, weaker nail, reflecting an extended phase of reduced support during growth. And those vertical ridges, gradually becoming more pronounced over the years, are the clear signature of a slow decline in circulation, recorded lengthwise along the nail in the same direction it grows, precisely because the process never paused long enough to create a horizontal mark. When you think about it this way, the nail becomes something quite unique. Hair grows and is cut away, removing any record it might have held. Skin constantly renews itself, shedding its outer layer every few weeks and erasing any lasting trace. The nail, however, preserves its history. Instead of discarding what it produces, it steadily pushes older material forward, keeping a continuous record intact. Each narrow strip across its width represents roughly a week of life as it formed. It is the only tissue that documents its past and keeps it visible. When you angle your hand toward the light and notice those ridges, you are essentially reading a report written months ago by the Matrix and never erased. For me, looking at my own hands changed from a simple habit into something more observational. I find myself pausing, studying the lines as if they were text. The nail records its story consistently, month after month. This leads to the final question: what actually wrote that record? The answer lies in the same biological processes that quietly affect every part of the body, even when they cannot be directly observed. When you connect all the pieces, they point back to a single underlying cause. The microscopic vessels above the matrix gradually lose their ability to produce nitric oxide, causing them to tighten slightly. This is the same endothelial change that occurs in small vessels throughout the body. Their walls stiffen due to the gradual cross-linking of sugars and proteins, the same process that affects the lens of the eye and the large arteries over time. Meanwhile, the stem cells within the matrix also experience gradual decline, dividing less efficiently as they age, influenced by the same reduction in cellular energy systems and internal repair mechanisms. Vessel function, structural bonding, and cellular activity all decline together, shaping the final result. These are the same biological patterns seen across organs you will never directly observe. It is important to recognize a boundary here as well. The general processes affecting the matrix are well supported and widely accepted. However, whether these changes occur at exactly the same rate in the nail as they do in larger structures like arteries or the eye is not fully established. The overall direction is clear, but the precise timing may vary. The nail stands out because it is one of the few places where these internal changes become visible. Arteries may stiffen without obvious signs. Cellular energy may decline without notice, and vessel function may weaken silently. The matrix experiences those same changes, but does something unique. It records them in a way you can see. Raise your hand and tilt it toward the light until the ridges cast a faint shadow. They run from the cuticle to the tip, each marking the boundary between a column that maintained its pace and one that slowed down. That slowdown occurred because the tiny vessel feeding it narrowed, influenced by the same endothelial decline and molecular cross-linking that affects circulation elsewhere. Reduced delivery of nutrients, including iron needed for DNA replication, led to slower cell division. The production of keratin in that strip decreased, while neighboring strips continued normally. The difference appeared over time as a ridge you can both see and feel. These ridges were once dismissed as simple cosmetic changes, but they represent something far more meaningful. They are a record produced by the matrix on one of the only surfaces of the body that preserves such information. That record reflects the combined activity of your circulation, your nutrient delivery, and your cellular function over the past several months. When you look at those ridges, you're seeing aging, but more precisely, you're seeing its written record. The ridges are the transcript.